So today, what are we doing? We're doing solving of first order differential equations. So dy dx equals some sort of function in terms of x. So it could be x squared plus 3, for example. So it's a function in terms of x squared plus 3. And then you can do something with that, and that's what we're focusing on today. Differential. Want to get the general solution for this equation. So first step, let's bring this bit over to the other side of the equals. What do you think we do next if we're going to get the general solution for an equation? Yep, so we can split the dy and dx up. So we could multiply both sides by dx. So we've got this now, and we want an equation in terms of y and x. So we can integrate both sides. 1 integrated in terms of dy becomes y. So it's currently the power of 0. So you add 1 to the power, becomes y to the power of 1. You don't need a plus c on both sides. So we can just have plus c on the right side. So eventually we'll have a plus c after we do this integration. Negative 4x, yep, so we add 1 to the power, and perfect. Okay, and don't forget the plus c. And why do we have the plus c, do you remember? There could be a constant, so if we went back the other way, we derived, that constant would disappear. So we don't know if there's a constant. And that's what makes it the general solution. We don't know the constant that could be there. And that's where the particular solution comes in. They give us a situation to determine the constant. So usually this application is when we're doing dynamics or kinematics. So like you're finding velocity from acceleration and you don't know the initial velocity. And that's the constant. And that's when you turn your velocity general solution into a velocity particular solution to find that initial velocity. F dash x, which is the same as, in terms of, you can call it y. That's usually what we use. dy dx. Yeah, correct. So again, the same thing. This time it's already been rearranged for us, i.e. the x is already over to the other side. So we're just finding, bring the dx over to the other side. Right. Oh my goodness. Thank you. Okay, and then integrate both sides. dy becomes y. Anyone remember this integral? I'm going to do when the derivative is present. So I'm going to let the function inside the power, which is a half, equal to u. du dx becomes 2x, and that hence the derivative is present. There's just no 2. So rearrange that to get dx by itself, and this is now going to hopefully cancel out the x's, so we're just left with whatever's underneath. So this becomes the u. and this is, we substitute, instead of dx, we substituted that in, so the x's cancel out. So we got 1 over u square root, which is the same as u to the half, du. So what does that integrate to? We can bring the 2 out the front. So we add 1 to the power, and we divide by the new power. So I added 1 to the power, I divided by the new power. Does everyone see that? I also brought this 2 out the front because it's a constant. Is everyone okay with that? So you're just left with u square root. Oh, there should be a plus c. Don't forget the plus c, I'm not worthy. It really depends on the mark scheme. Okay, so we found the general solution for y in terms of x through integration, through rearranging the differential. But it wants us to find the particular solution, so in this case we have to go one extra step. We have to sub in x equal to and y, or the function, equal to 1. So y, or the function, probably should call it, let's call it function, is equal to 1, and x is equal to, does everyone remember what I said? 6. So 6 squared plus 64, look at that. It conveniently works out to be 100, which is square root of 100 is 10. Bring that over, you have negative 10. Negative 9 is equal to c, or c is equal to negative 9. So therefore, the particular solution for the function is this bit, and you change the c to -9.